Hello, my name is Ethan Wilcox, and I'll be discussing today how structural supervision improves few-shot learning and syntactic generalization in neural language models. And this is work done with an array of collaborators across a number of different institutions. All right, so language models, which I'll be treating as functions that assign probabilities to strings, are at the core of NLP research. And there's lots of evidence that neural network-based language models can learn a lot about the syntax and grammatical aspects of language. However, there are two kind of key properties of language that previous work hasn't assessed directly. The first of these is syntactic invariance, and by this I mean that humans can deploy the same grammatical rules across different syntactic frames, and I'll give examples of this later on. The second is few-shot learning capabilities. So humans can learn a lot about the grammatical aspects of a token from a single example of it in context. Now, the motivating questions for this work is what is the relationship between the amount of evidence and the strength of a syntactic generalization learned by neural LM? And can models transfer learned representations between syntactic frames? In addition, we look at the effect of structural supervision on training. So there's evidence showing that structural supervision helps learn syntax, especially in low data settings. And we'll be testing two properties of English, nominal number or subject-verb number agreement, as well as verbal argument structure. All right, let me move on to discuss our methods. So here's our pipeline. We take a training corpus and we train a neural language model on it. Now we want to ask, what has the model learned about specific lexical items? In order to answer this question, we employ what's called the psycholinguistic assessment paradigm. In this paradigm, we test the model by giving it two variants of a sentence, a grammatical variant, such as the client is, and an ungrammatical variant, such as the client are. We assess the proportion of times the model prefers the grammatical variant over the ungrammatical variant. And in this case, we take that proportion, we turn it into an accuracy score for each word, and then we can plot the accuracy versus the number of times that word occurs in the training corpus. So here's kind of like a sample chart for these learning curves with accuracy on the y-axis and the number of times that the word occurs in training on the x-axis. And if the learning curve looks like this, that's evidence of kind of rapid few-shot generalization. So after just a few exposures with the word, the model is displaying very high accuracy. If we see learning curves like this, then that's evidence of generalization, but it's not kind of very few-shot generalization. And if we see learning curves like this, then that's evidence that there's very little learning going on. In order to assess the syntactic invariant properties, we create similar tests, but we kind of switch the syntactic frame of the test. So for example, instead of having a stative sentence where the verb follows the noun, we switch these to be polar interrogative sentences where the verb precedes the noun. So is the client is the grammatical variant here, and are the client is the ungrammatical variant here. Now crucially, we only test nouns that occur in this kind of base frame in the training data. So success for these testing regimes requires generalizing to new syntactic frames. All right. The models we tested, so we have an n-gram baseline. We have a recurrent neural network enhanced with LSTM architecture that has kind of no obvious hierarchical bias. We have an action LSTM, which predicts the action sequence needed to constituent parse the sentence. We have a recurrent neural network grammar, which is similar to the action LSTM. It also predicts the action sequence needed to constituent parse the sentence, but crucially, it composes these partially built phrase structures with bidirectional LSTMs during the sequence prediction. And these two models are our structurally supervised models. So just a little bit more information about the training and testing. We train our models on the WSJ portion of the Penn tree bank. This is 1 million words. It's very small by contemporary standards, but we wanted really kind of high quality parse and part of speech statistics, and the PTB is hand annotated. For our testing regime, we sample words from 8 different exposure buckets based on their frequency in the corpus. And for each bucket, we get 20 words from each, or 20 tokens from each category, so say 20 singular, 20 plural. And for each of these 40 tokens, we create 20 test sentences that we actually run the tests on using templates. So just to give you an example of one such template, we might have the lawyers near the important petition is or are. This is our target word, lawyers. And then the other content words here are high frequency tokens. So they're words that the model has seen a lot during training. Okay, let me move on to discuss nominal number learning. So previous work has shown that models can achieve high accuracy for these subject-verb number agreement tasks. We kind of employ 3 tests. One is a simple test with no modifier, so the president is versus the president are. That's the ungrammatical variant. We also have a prepositional phrase modifier test, so the petitions near the old investment is or are, as well as a relative clause modifier, so the client that the lawyers like is or are. All right, now here are the results for this this experiment. On the x-axis, we have the number of exposures that the target token appears during the training, and this is on a log scale. And on the y-axis, we have the accuracy scores. The models are colored, and this is the same coloring that I'll use for this whole presentation. And then the panels are our different tests, and I've just kind of given you a little examples up at the top so you can remember which one is which. Chance is 50%, and there's a kind of blue line here so that you can see that very easily. The points here are the means and the 95% binomial confidence intervals for each exposure bucket. So that's kind of pooled across the accuracy for all the words in the exposure bucket. And the lines are regression fits on the raw data. So what we can see here kind of right off the bat is that, especially for the no modifier case, there's evidence of few-shot learning. So the models have seen tokens only 2 or 3 times during training, but they're 75% accurate. They're well above kind of baseline accuracy, and then they just get more accurate as the tokens appear more frequently in the training data. So moving to the modified tests, the models don't show such strong accuracy for the really low numbers, but they improve with exposure, and really the structurally supervised models kind of show greatest improvements with increased exposure outcomes. Okay, so let's move on to the transformed contexts. So as I said before, our transformed contexts are polar questions which invert the noun-verb order. So we test nouns in this case where the verb follows the noun in training, and in the polar questions, the verb precedes the noun. So to succeed, the models really need to learn that subject-verb number agreement is invariant to linear order. We have 2 tests here, a simple polar question, so are the president versus is the president, and then a polar question with a modifier, so are the big and very important hearings, and is the big and very important hearings. Here are the results using kind of the same presentational paradigm. So you can see here that the neural models are actually above chance in all of the exposure buckets. The n-gram model is below chance. But there's no evidence that the models are getting better with increased exposure during training. So the data here kind of suggests that the neural models have learned a number representation that's invariant to linear order, but there's lots of room for improvement. So humans have very strong intuitions, are the president sounds very, very ungrammatical to a human. Okay, so let me move quickly on to verbal argument structure learning. Here we're simplifying verbal argument structure just to ask, is a verb transitive, in which it requires a theme, which is frequently grammatically realized as an object, or intransitive, in which case it cannot have a theme. And we check transitivity using the kind of expertly annotated CellX dataset. So just give you 2 examples of tests here. One is an active infinitival test, so the doctor can cure the patient today, which is grammatical, and then the doctor can cure today. Our prediction is that today should be kind of lower probability following this, following no object after a cure, which is an obligatorily object-taking verb. We also have an active past tense, so the doctor slept today, and the doctor slept the patient today. Today here should be high surprisal in the ungrammatical case. And we have so we have verbs like cure in both tests and verb like slept in both tenses. It's not just that slept obligatorily intransitive verbs are just for the past tense test. They're balanced between the tests. Here are the results for this experiment. You can see that the models are well above baseline even for just 2 or 3 exposures, and then they get more accurate as they encounter more data in the training. Especially here, the structurally supervised models perform better. Now, we also find evidence that models can transfer this knowledge into passive voice contexts. I'm not going to discuss it here for time constraints, but please see the paper for more detail on that aspect of the work. All right, so just in summary, here's a table that kind of summarizes all the results with the tests here and the different models here. The fraction here indicates the proportion of exposure buckets for each test for which the model performs above baseline, colored by terciles. And then the tests for syntactic invariants are below this line here. Now we can see that neural models show evidence of few-shot learning outcomes. That is that they're performing kind of relatively well, that is above baseline in most of the exposure buckets. These results indicate too that the neural models can transfer some representation kind of across syntactic frames. However, there's room for improvement here. So these, maybe the models are performing kind of under what we would expect kind of human expectations to be. And then in addition, across the board, we see that the structural supervision helps with these tests, both for few-shot learning and for invariance properties. So thank you very much, and I'm happy to take questions in the Gather Town and the Q&A session.